So let us start this particular session on our field programmable gate arrays, or you can say FPG, and this is day one. So in our previous session, we have just seen the introduction. Yeah, notes and PPTs, daily PPTs will be posted in a group. Okay. Yeah. So in the previous session, we have basically given intro about what is the course and what is the expectation and what are we going to learn. That and all things we have seen in our previous sessions, right? Now, in this particular session, let us try to first of all establish the difference between something known as ASIC, that is application specific integrated circuits, and FPGAs. So let us try to understand the difference between these two. So before going to start about this differences, I hope a lot of you already know about what do you mean by an ASIC. So can anyone tell me what do you mean by an ASIC?
Application specific integrated circuit.
Okay, so ASIC basically stands for application specific. Any other answers?
In ASIC, you cannot configure it by yourself like FPGA. It is a fixed one. You cannot change the connections and all. It is a application specific, which is already configured.
The program itself.
Okay, so let's be interactive. You can openly discuss and you can give the answers. There is no problem, and no one knows you, so no one is going to think about you, right? So treat this as an opportunity to speak up and try to give your answers. Okay. Yeah. FPGA is reconfigurable. Yeah. So what is meant by reconfigurable? That is what we are going to see. Yeah. Any other answers? Any others wants to give the answers? What do you mean by? So basically, this ASIC stands for ASIC is nothing but it's an integrated circuit that is a custom design for a specific application. Okay. So it is basically designed to perform a fixed or dedicated task. Okay. And this cannot be functionality cannot be changed after fabrication. After you have fabricated an ASIC chip, it's not easy to change that particular configuration, and it is optimized for performance, power, and area, and used when the design is finalized and produced in large volumes. Like if we want to produce the chips in large volumes, we prefer this ASIC, right? Now, can anyone give me any applications of ASIC? Have you seen any applications of ASIC anywhere? Smartwatch, decoder, okay. Any other applications where you have seen your ASIC chips? Aerospace applications, some toys, or your mobile phones, right? So in our mobile phones also we microcontroller, okay, washing machine, okay. Any other examples? Have you anyone have seen any other applications where you are using your ASIC? Yeah. So basically, as we have discussed, this is smartphones exactly. So basically, these are you only use it for any a particular specific application. If you want to develop it for exactly digital computer, exactly. So if you want to design or if you want to use it for a specific application, you are going to build this particular ASIC, and it is only fixed for that particular dedicated task. Like let's say suppose if you want to use it for some signal processing or some image processing, then it is only dedicated to that particular image processing. It cannot be used for another signal processing or something, right? So it is only for that particular task. Okay. Yeah. So this is one example where you can see your asset like your mobile phones. Okay. So this is a very good example. We in our smartphone camera, we use one ASIC chip, which is image signal processing, and it is a like for example, it is used. The features of that particular chip is for noise reduction, autofocus, and auto exposure, and HDR image merging, and color correction. Like let's say suppose for this particular application, we need to develop a chip, or we need to develop a chip. Where if we are going to prefer an ASIC chip, then it is only for this particular applications. The features of this particular chip will be these features. Okay. So this is where one example where we can see about this example of one ASIC. Okay. So this chip is custom designed only for image processing. That's it. Okay. And it does not run general programs like a CPU, and it's not reprogrammable also. What do you mean by reprogrammable like an FPGA? If you don't know, don't worry. We will discuss like what do you mean by reprogramming? and how we are basically achieving this reprogrammability in an FPGA. That and all things we are going to see. And one of the ISP ASIC is fabricated. So once this ISP ASIC, so it is known as this particular ASIC chip is known as image signal processor ISP. Okay. So if it is being fabricated, its functionality cannot be changed, and it is always going to perform the same image processing pipeline. And any improvement requires a new chip version. We cannot add the new features like in our software upgrades. Like we cannot upgrade the chip. Okay. So if we need any new revisions, then we are going to another new chip. For example, every year we will get new prototype chips, right? So in our mobile phones, or you can also see in your like Samsung and Apple will release their new chips or new phones with new added features, right? So every year, so you cannot configure it using your software. Like your software, you cannot update it for every 6 months or every 1 month. So if you want any new revisions or any upgrades in your chip, you need to fabricate it accordingly, and you are going to release. So this is nothing but your application specific integrated circuits. I hope this is clear, right? Any queries or any doubts in this ASICs? So these are basic points. I hope you all know already, right? Anyone, any queries in this ASIC? Great. So let us move forward. Yeah, we will come to that. How to build an ASIC, that and all, and what are the teams which we need, and what are the tools which we need. We'll come to that particular thing. Okay. Now, so why an ASIC is used? So yeah. Like let's say suppose you have two options. We have ASICs and we have FPGAs, right? We have classified. So your ICs are basically classified into two types. One is ASIC, which is only for specific purpose, and one is FPGAs, or you can say as PLDs, programmable logic devices, which are basically configurable. Okay, configurable in the sense you can configure the feature. Like if let's say suppose it is use it for some image processing thing, then you can configure it, and you can also use it as an audio processing thing. Okay, by changing bit file and all. We will see later. Okay. Now, the main question arises is like, why do we prefer ASIC? Like, we have this much of configurability, right? So, if we are having a chip which is basically used for configurability, which has a feature of configurability, then why we are using ASIC? Anyone has any answer for this? You are having a chip with you which is basically configurable. Then, but why we are using this ASIC? Exactly. One of the reason is cheaper than FPGA. Exactly. Even though FPGA has configurability in it, ASIC is cheaper compared to FPGAs, and also area in terms of area also, uh, ASIC needs less area compared to FPGAs. Okay. For a specific task or for a specific program or for a specific purpose, you are going to use an ASIC. So accordingly, you are going to manufacture it. Let's say suppose it is going to take this much of area. Let's say A1. Coming to FPGA, for this same process or for the same task, it will require more than the specific area. And one more thing is the utilized area will be less. We are going to have this much area, but the for this particular task, for a task T1 or for any application, if we are going to use an ASIC, we are going to use this much area. But using this FPGA, we are going to occupy this area. But in this area, we are going to utilize this much of area. That's it. Okay. We can also reduce the area which is needed. In FPGA also, we can reduce the area which is needed by using some techniques. But the overall area will be this much. Available will be this much, but the utilizing will be this. Okay. Yeah, we will come to that. We will come to each and every question which you are going to ask, which is present in our next slides. Okay. And coming to lower power consumption, yes, that is also correct. And someone has commented, yeah, for mass production also. Exactly. So is it clear why we are basically using this ASIC when we are going to compare with our FPG? Is it clear? So basically, this ASIC is used for image. For example, in this particular example, only we are using this ASIC for image processing, right? So for image processing, that must be really fast. Let's say suppose if we are taking a picture, and after taking your picture, let's say the camera or whatever the mobile phone you are using, it is going to what to say, let's say if you are going to take it in a portrait mode and it needs to blur your background. So if it is taking 1 hour, then are you going to use that mobile phone? No, right? So it should do that particular process in few seconds, right? And let's say suppose if you are going to use that camera and if it is consuming 50% of your mobile phone's battery, then you're going to throw away your phone, right? So it must be very fast in terms of your time, and it must be low power consumption, and it is also going to use in not only one or 10 phones, right? So it is that particular chip should be used in millions of phones. Okay, so for high volume consumption, your ASIC is preferred. Okay, and so this also matches your ASIC characteristics, like it is only used for application, and it is going to have a fixed functionality, and it is optimized for performance, power, and area, and it is used when the design is finalized and mass produced. Here, the important point over here is the design is finalized. Whenever the design is finalized and it is needed to be mass produced, we are going to use our ASIC. Okay. So this is where we are going to use our application specific integrated circuit. And as the example we have seen, so characteristics are high performance and low power consumption, and smaller silicon area, and high initial development cost, and economically only for large scale production. Okay. So some of the examples you can see is mobile processor chips and network switching and graphic process. Okay. So this is about your application specific integrated circuits or ASICs. So is it clear for everyone? Did you get a brief idea about where you are going to use this ASICs and why you are going to use this ASICs? These two are very important points to be noted, because where and why are very important. Why you are using and where you are using. So in interviews also, most of the people are going to ask you where and why. Are these 2 points clear? Any doubts or any queries in this? Now, coming to this particular thing, which is known as PLD. PLD basically stands for Programmable Logic Device. Okay. So, in the case of your ASIC, once the chip has been designed, you cannot basically configure it, right? But in the case of your PLDs, it's a type of integrated circuit where the functionality can be programmed or reprogrammed by the user after manufacturing also. Okay. So how, sir, how we are going to reprogram it or how we are going to reconfigure it? That is what we are going to learn in our sessions, right? So PLDs basically have this particular feature which is known as configurability. Okay. Now, how we are going to configure or how we are going to configure the behavior of your hardware is using the HDLs. HDL is nothing but hardware description language. We have two type of HDLs, Verilog and VHDL. Okay. So Verilog is popularly used in our India, and VHDL is popularly used in European countries. Okay. So our main target will be Verilog. So your prerequisites should also be in your Verilog. So if you don't know this Verilog language, also no issue. So you can refer to the playlist which is available already in our channel. From the basics to the advanced versions, everything is available. So you can refer. Okay. We are not going to deal with VHDL. So we need the prerequisites to be in Verilog, right? So we are going to define our hardware which is present in our FPGA using Verilog. Okay. So this is ideal for prototyping, learning, and low to medium volume production. Like let's say suppose if we are developing a chip, and if we are developing a chip, let's say for example, some for FIR filter, previously someone has said, so they have done one project on FIR filter implementation. Like let's say suppose if you are going to develop that particular feature on a chip, so instead of directly fabricating that particular chip, you can test it, or you can just test the prototype on an FPGA, because you can basically perform multiple times reconfigurability. Okay, so using an FPGA, you can check for multiple number of times whether your expectations are being met or not. So if they are not meeting your expectations, you can again you can again basically reconfigure it, and you can basically check it, okay, for multiple number of times using an FPGA or any programmable logic device. Okay, so this is where you are going to use a programmable logic device compared to your ASIC. Now, if you feel that all your requirements are met, then you are going to implement that same program on an ASIC. Okay, so this is where your PLD will come into the picture, and you're going to use it, and also for learning purpose. Like in many of the universities, in some well-known universities, you will have this FPGAs or PLDs. Basically, you can learn, like you can learn how the process is being happening, like how you're writing the code and how you're dumping the code and how the routing and all the stuff is going to happen. You can basically learn that. Okay, so this is where your PLDs will come into the picture, right? So is it clear? Any doubts or any queries? So Verilog, system Verilog is basically used for verification purpose. That is entirely different, like where we are using. I will explain when we are going to have that particular sessions, right? So system Verilog, you cannot partially you can implement on the hardware, but completely you cannot implement it on the hardware. So it is only for completely verification in software terms. Yes. Any other queries? Shall we move forward? Yeah. So, for example, if we are going to have this network router card, so what is this chip is basically going to do is it is going to have the connections with multiple LANs, and it is going to route like which particular system should be connected to which particular system, right? So it is going to follow the Ethernet protocol, Ethernet using the particular protocol MAC layer and data link layer. It is going to choose, and it is going to decide which particular connection should be done. Okay, basically it is routing the things. And if you want to implement this particular chip, then you're not going to directly, if you want, you can directly implement it on an ASIC. But instead of that, many companies, what they do is they basically develop their prototyping on an FPGA chip, and they test it. And after that, if they feel if it is correctly working, then they are going to the mass productions in terms of your ASIC, right? So this is where you can expect an FPGA or an PLD is going to use. So a network router card is a plug-in circuit board inside a router that is basically going to receive the data packets from the network links. That is what I've said you previously. And it is going to process the packet headers, and it is going to decide where packets should go next, and it is going to send the packets out through the correct interface. For example, if we are going to have multiple systems like this, in layman terms, if I want to speak, this is my router, and I'm going to have multiple systems over here. So this is basically routing me where this particular system should be connected and to which system one system should be connected. Okay. So this is somewhat in layman terms and how it is going to happen, everything. So if you try to understand this Ethernet protocol, you will get to know. Okay. Ethernet protocol where we are going to use the header information, and there will be so many particular things which we are going to filter, and we are going to decide the exact path. Okay. Yeah. So that is not our concern. We are going to basically understand how and where your PLDs can be used. Okay. Yeah. So this is what it is going to happen on a router card. So basically, a packet arrives from a fiber, and physical layer is going to convert the electrical signals into digital data. And packet parsing, like you're going to divide your frame into IP layer and MAC layer and VLAN, and you're going to forward the packet based on the routing tables. And packet is queued and scheduled, and packet is transmitted to the next hop. So this entire process should be happen in nanoseconds, and that too in very high data rates. For example, if we have connected to a particular network, and let's say if you are connected to a something, let's say internet network, and if you are trying to open a YouTube video or something, and if it is getting buffered for long times, then it is not correct rate. So it should happen in very nanoseconds. Okay. So this is where you can also use your PLDs for your testing purpose. And you can also use this PLDs in advanced driving systems, ADA. So do you know this particular, I think, Tesla company car? I think most of you know about that particular automated cars. Yes, in the chat box.
Yes, sir.
So apart from this Tesla, any other companies do you know, like which is basically following this ADA systems, advanced driving systems? BMW, exactly. I think I've seen like in Tata cars also, Tata or Mahindra, I don't know exactly. Volvo also, yeah, exactly. I've seen one feature like you can set some, yeah, exactly. Honda also. Okay. So let us take a case scenario over here. Let's just suppose you are driving an automated car, right? So what do you think? What are all the features or what are all the sensors you need to have for that particular thing? Like let's just suppose you are developing a automated car, then what type of sensors or what type of features you need to have for achieving the automation? Nice, nice. Okay, cruise control. Okay, so let's say, let us take example of our brain only, right? So we think, let's say, suppose we are walking on a road, right? So our brain is going to process a lot of information. Like, let's say, if we are going to see a shopping mall, or if we are going to see a tree, or let's say, if we are going to see a vehicle which is going, our brain is going to process like what type of company vehicle it is and what is the logo. And using the logo, we are going to identify what type of vehicle it is. And roughly we can also estimate the speed which it is going. So this much of information our brain is processing using the sensor, using the information which our sensors are giving, right? So our car is also going to have one processing unit which is going to process this much of information which our sensors are giving, right? So whatever the sensors you have mentioned, that particular information it is going to give. Okay. Let's say suppose this particular car, whatever the automated car you have mentioned is present over here. My drawing is very bad. Sorry for that. So let's say if it is going over here, and let's say if some obstacle suddenly comes into the picture. Okay. Now, for example, if this particular process, if the particular control unit which is present in this car, the sensor will do it work. It will immediately detect the obstacle which is present. But that particular information should be given to the control unit, right? And the control unit, after taking the particular information, it should process immediately, and not that it is going to process that information which is given by the sensor, and after 1 hour it is going to give the response, then the damage will happen, right? So here the information which is given by the sensor should be processed immediately. Within fraction of seconds, it is going within nanoseconds, it is going to process that particular information. Not only a sudden information, it is going to process the information for each and every second. Right? Am I right or wrong? Yes or no? Yes. So here in this particular cases, our assets, or you can also use our FPGAs, right? So or PLDs. So basically, these FPGAs are very high processing chips. So why these are high processing and fast processing, we will discuss. Okay. So in this particular cases, you can use this particular FPGAs for developing this particular control unit. Okay. So we'll see that particular thing. So this is what we are discussing previously. So ADAS systems are electronic systems in vehicles designed to assist the drivers, improving the safety and reducing human error. And this systems uses sensors, control units, and software algorithms for monitoring the environment and vehicle behavior. Okay. So core components, you have said it correctly. The sensors which we are going to have radar, lidar, and cameras and ultrasonic sensors. And we are going to have the ECUs. So these are basically embedded computers that process the sensor data and make real-time decisions. For example, ECU controlling automatic emergency braking or lane keeping. Okay. And you can also use your actuators. So basically, these are going to use control the vehicle mechanisms based on the ECU commands. Okay. So this and all the things which we are going to have. And the main question is, what is the role of PLD in this particular ADA? So basically, this PLDs like FPGAs and CPLDs, which stands for complex programmable logic devices, are widely used in our automotive electronics, because they allow customizable and very high speed and parallel processing for safety critical and sensor intensive applications. And but we cannot say we are using it because there will be another factors also. There will be industry safety standards, and there will be many checks before going to use this FPGAs in actual applications. But theoretically, up to some extent, we can use this FPGAs because of their high parallel processing and very high speed and customizability. Okay. So this is about your PLDs, and this is the differentiation table between your PLDs and ASICs. Okay, so where the purpose of your PLDs mostly use it for prototyping. As I've said, this can be only used for prototyping and algorithm development because there will be lot of industry standards and lot of testing and lot of requirements where our PLDs may lack, and we are not going to that particular subject. And coming to your assets, these are used in production vehicles for final ADA implementation, whereas your prototyping, you can use your FPGAs. And coming to performance, these are very high speed. Your PLDs are very high speed and parallel, but generally less optimized than your ASIC for power, cost, and size. And ASICs are highly optimizable and flexibility. You can reprogram for updates or new ADA features, but your ASICs are fixed, and cost is more compared to your PLD, compared to your assets. Your PLDs will cost more. And use case, you can use it for developing simulation, testing of new algorithms like lane detection or sensor fusion. And coming to your assets, you can directly make it as a product and you can deploy it in your ADA unit or the control unit. Okay. Yeah. So, is there any doubts or any other queries till now? Yeah, exactly. That is what we are going to get into the next question. So, as I was saying, FPGAs will cost more, FPGAs will cost more. So, this point we have raised. But why these are going to cost more is that we are going to discuss after discussing about the FPGA internal architecture, right? So, after discussing about this FPGA internal architecture, what is actually present in this FPGA internal architecture and what is that it is making this FPGAs configurable, then I think it is better to discuss this particular points, why FPGAs are less optimized and why FPGAs are more costly. Okay. So this points already included in this particular two slides, but I don't want to discuss it now because we don't know exactly what is present in FPGA. And if I discuss it now, then it will not be a good idea because many are new to this particular concept of FPGAs and they will be zoned out. Okay. So that is what I'm thinking, and that we will discuss when we have completed our internal architecture discussion, right? So yeah. So in our today's session, we have basically focused upon what do you mean by an ASIC and what do you mean by an FPGA and what is the differentiating factor between your FPGA and ASIC, and where you can see this ASIC and where you can use this FPGA and some of the applications of FPGA and some of the disadvantages of FPGAs, right? So yeah. So this is what we have discussed in our sessions. Can we integrate all the sensors here? Where do you want to integrate? I didn't get your question. Yeah. So this is about this particular session. I hope you have got a clear idea about the differences between your FPGAs and ASIC. And yeah, so that's all about this particular session. I hope it is useful for you guys. And tomorrow we are going to see the ASIC design flow and the FPGA design flow, how you are going to design an ASIC chip, what is the flow you are going to follow, and what are the tools you are going to follow. And for FPGA design flow, what is the flow you are going to follow, and what are the steps you are going to follow, and what are the tools you are going to follow. And we are also going to classify the FPGAs based on the companies. Okay. So before that, we are going to first of all see the internal architecture. That is very important. And I hope my pace is also slow and it is not speed, right? Please, can anyone tell me? Is my pace okay or is it speed? It is okay for everyone, right?
Yes, sir, this is
Yeah.
fine.
Okay. Great. And I'm planning the sessions for at least 30 minutes, 30 to 40 minutes. This is the time limit which I'm going to fix. Okay. Yeah. And we will go slowly. We can extend the sessions also. There is no issue in that. We will go from the very basic level to we will see up to what level we can. Okay. So that is my style of teaching. Yeah. PPT will be uploaded. It will be converted into PDF and it will be uploaded in the group. Okay. Can we optimize PPA and FPGA? Exactly. We can optimize, but up to some extent we can optimize, but not up to great extent we cannot optimize it. We can also optimize. Yeah. Okay. Yeah. So if you are going to have any doubts or any other queries or any other things you wanted to discuss with me, you can stay in the meeting or else you can leave the session. Okay. Thank you. Good night.